This video will present the ExVis program, which is a data visualization tool for exploring the measured response of test structures. ExVis was designed to provide for experimental test data what a graphical post-processor provides for the results from finite element analyses. The ExVis program was developed using a test bed of data collected from 20 load tests on large pre-stressed concrete girders that were conducted as part of a project sponsored through the U.S. National Cooperative Highway Research Program. Each of these girders was 6 foot deep, simply supported over a 50-foot span, and subjected to a uniformly distributed load using 44 hydraulic jacks. Each of the test girders was extensively instrumented. This included approximately 30 displacement transducers, up to 150 strain gauges on reinforcement, and up to 50 concrete surface strain gauges. Handheld devices were used to make relative displacement measurements over the entire length of each test girder at key points in their loading history. The image on the lower left shows a grid of small light-emitting diodes, or LEDs, that were spaced on 5-inch centers on the surface of the web of a test girder. The XYZ coordinates of each LED were recorded by a Krypton camera to an accuracy of about 1/1000th of an inch. This provided an unprecedented level of experimental test data that is analogous to nodal displacements from a finite element analysis. The ExVis program was written to integrate all aspects of the measured response of test structures with the geometry and other properties of these structures as to further the understanding of their measured response. A demonstration of the ExVis program is now used to describe the capabilities and potential for such experimental data visualization and analysis tools. Upon opening the test file for Girder 9, ExVis displays a front elevation view of the left end of this girder. The location of the supports, draped strands, stirrups, and top loading jacks are shown as I pan along the length of the girder to its right side support. Selecting View and then Control Show from the top menu opens the dialog box for controlling what is displayed. Using the Control Show dialog box, I will illustrate that all parts of the structure are objects by turning off and on the display of the girder, slab, strand, and stirrups. The loading jacks and all measurement instruments are also objects. These have data values at each time step in the loading history. I will turn and leave on the stirrup strain gauges. I will now open the View Data Curve dialog box, which is used to examine plots that are selected by the user. I will drag the cursor along the load deformation response. As the load increases, the development of cracking is shown. Each of these cracks is also an object and was measured using photogrammetric methods. I will go back to the Control Show dialog box and click on the Selection tab. By choosing the Stirrup option, I can now select specific stirrups on the structure. When I select a stirrup, the measured strain in each of the 4 gauges along that stirrup is shown, and in which the length of the displayed horizontal line is proportional to the measured strain in the associated gauge. This is useful for understanding how shear cracking influences the development of stirrup straining. I will change the selection option to cracking, and then select several cracks that run along one diagonal line. I then go to the top menu and select the Free Body Diagram option, which will form a free body diagram based on the location of the selected crack. The metadata for the stirrups contains their stress-strain relationships. This makes it possible to calculate the force carried by the 13 green stirrups that were determined across the crack. I can plot the measured stirrup contribution, Vs, against the applied loading, and this illustrates that the stirrups did not carry any significant force until after shear cracking occurred. I can also plot the concrete contribution to shear resistance as a function of the applied loading, in which Vc is the difference between the total applied shear force as calculated by the forces in the top jacks and that which was calculated to be supported by the 13 stirrups across the crack. I will now turn off the Free Body Diagram viewer and deselect the strain gauges in the stirrups. I will now select the LVDTs, go to the Data Curve viewer, and choose to view the calculated web shear strain within one of the LVDT rosettes. Either the complete load strain response or the envelope of the measured response can be selected to be viewed. I will now go to the Control Show dialog box, deselect the LVDTs, and select the concrete surface strain gauges. I will now choose to examine the measured response from 4 concrete surface strain gauges, which I select by clicking on each of these gauges. To view the measured strain from one of these gauges, I select the concrete gauge viewer and then choose diagonal gauge E3, that is located just inside of the support. The load versus compressive strain in this gauge is now shown in the data curve window. By scrolling along this curve, it can be seen that as cracking developed above the gauge, that there was a rapid increase in the strain measured by this gauge, presumably due to a reduction in the stress that could be transmitted across the cracks above this gauge. Just prior to failure, the compressive strain in this gauge was approximately 2900 microstrain, indicating that crushing was imminent. The ExVis program can also be used to examine the data collected by the Zerk gauge system, in which the horizontal, vertical, and diagonal displacements between aluminum targets located on a 10-inch grid were measured at